Let's go through activity 2. So in this activity, your main goal is to get practice just making sure that the reg class package has been installed and that you can run the associate command and talk about the outputs. So once you've installed the prerequisite packages and installed the reg class package, you'll always need to do library reg class when you open up RStudio. Just because you've installed it doesn't mean everything's available. You have to invoke the availability of everything with library reg class. Once that's done, you won't see any output, but all of the data sets, all the commands that are inside that package will be available. All right, question 1 wants you to look at the Survey 11 dataset. So in the past, we've downloaded files and read them in with read.csv. Since Survey 11 is actually built into the reg class package, we can load it up just with data survey. So I'm going to click run, and you'll notice that Survey 11 is now in the data tab in the global environment. So this contains information about Stat 201 students from a few years ago, and we're going to analyze the potential association between someone's relationship status and their gender. And we might be interested in knowing, does knowing someone's gender kind of narrow down what they think their relationship status is? All right, so if an association existed, that means that men and women kind of view relationship statuses somewhat differently, because you would expect them to have the overall same distribution of if they're single, in a relationship, etc. here. All right, so we're going to use the command associate to do all aspects of the analysis. So the way that associate works is we type in associate, and then in the parentheses, in general, it is the name of the y variable, twiddle, the name of the x variable, then a comma, data equals, and we say where the data actually is. I'll just put a placeholder capital data here. And then there are some optional arguments. One argument is permutations, which is going to specify the number of permutation data sets that are used to estimate the p-value. By default, it is 500. If you want more, you'll have to specify more. If you just want 500, then you can leave this argument out. And another argument is seed. Now, since the permutation procedure is a random procedure, it's randomly pairing up the observed values, then every time you run the command, you're going to get a different estimate for the p-value because you'll get a different set of permutation data sets. Now, if you want to reproduce your results, then setting the random number seed is what you need to do. So in this case, I'm going to say, let's set the seed equal to 2011. In general, you can set it to whatever number you want. Every time that you use the same number, you'll get the same results. If you use a different number, you'll get a slightly different result. And so let's go ahead and fill in the pieces here. Our y variable, I say, is x34 relationship status. So I'm going to go ahead and copy and paste that. The name of the x variable is gender, x02.gender specifically. So I'll copy and paste that. And the data frame in which these are living is the Survey 11 data frame. And I'm going to go ahead and delete this permutations equals 500 because by default it'll do 500 anyway. All right, so I'm going to delete that, and I'm actually going to show you an error that happens if you're not too careful. So this bottom right-hand window is where the plots are made, and if you try to make a plot that's so big that it doesn't have space for it, well, it worked for me, so let me see if I can actually make it even smaller. You might get an error that says, nope, I can't make that plot for you. So if I do this, notice it says error in external graphic state. You can't do it. All that means is that, hey, you didn't give R enough room to actually make that figure. So easy fix, you just resize the window, you can redo that command. Okay, so does the mosaic plot suggest an association exists? All right, so an association exists when knowing the value of x narrows down the possible values for y that we might observe. So overall, the marginal distribution of relationship status is the segmented bar chart on the far right. Now, if an association exists, we should see differences between this marginal distribution and the conditional distribution for females and for males. And indeed, that's what we see. We see there is a slight difference in the conditional distributions of relationship status between genders. And in fact, kind of interesting here, a larger fraction of men said that they were single than women. Kind of an unusual discrepancy. Now, we'd like to know, okay, is that discrepancy real? Or can it be just readily explained by the nature of collecting data and chance variation? All right, so does the mosaic plot suggest an association exists? Yes, the conditional distributions of relationship status looks to be somewhat different between genders. So for example, a higher fraction of men report single than women. Those are the blue bars there. All right, so we see some difference, but we expect some difference because it's just a sample. There's chance variation when collecting data. And so we'd like to know, is this difference real? Is the discrepancy we see in these conditional distributions something that can be explained just by chance, or is it indicative of there being a real difference? So what is the estimated p-value of the discrepancy between these conditional distributions? Well, we've invented a number that captures what the discrepancy is. And in this case, that number is about 9, where this red line falls in this histogram below the mosaic plot. So what this plot is telling us is that during the permutation procedure, when we take the observed data values and randomly pair them up together so that there is no relationship between x and y, we see values for the discrepancy between 0 all the way up to about 20 or so. Now the value that we measured is right at about 9, and we see that that's fairly unlikely to occur just by chance when values are randomly paired. It's not impossible because we see some cases where we do get larger discrepancies by chance, but the vast majority of the time we see that the discrepancies in conditional distributions are somewhat smaller. So the p-value is what we use to determine whether or not the relationship is statistically significant, unlikely to be produced just by chance. So what we do is we look at the p-value of the discrepancy, and in this case, based on our 500 permutation data sets, we estimate that p-value to be 4.4%. Now, because this is just a simulation, we've only looked at 500 different permutation data sets where they're paired up at random. We've only nailed down the p-value to a small range here. In fact, the next line of the output says that after 500 permutations, we're 95% confident that the p-value is somewhere between these two numbers. Now, unfortunately, this means our test is inconclusive because we say something is statistically significant if the p-value is less than 5%, but some of the numbers in this range are less than 5% and some are bigger than 5%. So we don't really know, is the p-value bigger or is it smaller? So the test is inconclusive because the p-value is somewhere between 2.8% and 6.6%. So we are not sure if it is below or above 5%, that threshold that we use to determine statistical significance. All right, so how do we fix this? How do we make the test conclusive? Well, we need to up the number of permutation data sets. The more permutation data sets that we make, the better and better we've estimated the probability of observing at least as large a discrepancy just by chance alone. And so that's where we go and we modify our associate command by adding in the argument permutations equals to a larger number here. So it doesn't matter where in the command I put it, but I'm going to put permutations equal. And in this case, let's make 1500 as specified in the instructions. And we'll click run. Same mosaic plot because the original data hasn't changed. Different histogram because we have more permutation data sets and a better idea for what the values of the discrepancy happen by chance. And we have a more accurate estimate of the p-value. The range of p-values to which we've narrowed it down to is somewhat smaller. And in fact, what we notice is that all of the p-values here are below 5%. So we've narrowed down the p-value. We know it's less than 5% here, so the test is conclusive. And since the p-value is less than 5%, there's less than a 5% chance that we would have observed such a large discrepancy in the conditional distributions just by chance alone. The better explanation is that fundamentally there does look to be a difference in the distribution of relationship status between genders. So we say the association is statistically significant. So yes, the p-value is between 2.1% and 3.9%. This is less than 5%, so the association is statistically significant. All right, great. All right, so that's our analysis when we're studying the association of two categorical variables. Pretty straightforward. Look at the mosaic plot to see if this difference is large enough for you to even care about, if it has any practical significance. And if it does, follow that up with a test of statistical significance. See what that p-value is, the probability of observing at least as large of a discrepancy between conditional distributions as what you collected in your data. All right, question 2 deals with the friendship analytics survey. And the first thing you need to do is to download the act2-friendpotf.dat to your BAS320 folder. So you don't open it up. You don't open it up in JMP or anything like that. You just literally move it to your BAS320 folder. And then you delete this hashtag so that when this document is knitted, it will read in that data file. So the command's already there for you. We know that to get data into R that's in a file, we need to do read.csv, the name of the file name, and we need to give it a name. In this case, I'm saying let's name it FF for female friend. So we'll click run, and boop, I get an error. Why do I get an error here? I know that my Act2 file is inside my BAS320 folder. What happened? Well, it looks like currently R is looking in a different folder here. It's in my 471 capstone class. And so I need to make sure that I change that folder into my BAS320 folder. So I'm going to go to Session, Set Working Directory, and I'm going to choose my directory. And I'm going to go, and I've actually have subfolders here. I'm going to go into my Activity 2 folder where I see act2-friendpotf.dat is there. Okay, so I'll click Run, and there we go. FF is in there. Here's all the columns, and let's do some analysis. So what we're going to do is we're going to compare the typical value of the friendship score between two or more different groups. So we need to know, are we comparing averages or are we comparing medians? So we determine this by looking at the shape of the distribution of our variable here. So we're going to look at a histogram and a QQ plot of the variable friend score. So hist is invoked by the command hist. I give the name of the data frame, then a $ to refer to a particular column, and friend score is what I want. So I'll run that. And it's hard to tell whether or not this distribution of values looks well approximated by one of those normal curves from the histogram itself. So instead we make a histogram, or sorry, a QQ plot. So once we make the QQ plot, we have a much better idea for whether or not we can approximate the shape of the distribution by one of those normal bell-shaped curves. And what we're looking for is how close these lines match up to this diagonal red line. If the points fell exactly on this line, then the values that we've observed match up exactly with what they should have been if the data actually did have a normal distribution. Now, we never actually expect it to fall exactly on the line. That's what these upper and lower dotted bands for. They provide you a little bit of leeway. So as long as most of the points are inside the upper and lower dotted bands, you're always going to find some points on the outskirts on the left or to the right just being a little bit outside, even if it is normal, so that's fine. As long as they're inside this upper and lower dotted band and there's no systematic, obvious curvature away, then we can consider the shape to be well approximated by a normal distribution. So in this case, I would say that, sure, it looks like the distribution of friendship scores is approximately normally distributed, and when something has a normal distribution, it's appropriate to summarize the distribution, the typical value, with the mean. We don't need to use the median here. So we will say the mean provides the better summary of the typical value because the QQ plot shows that the shape of the distribution of friendship scores is approximately normal. In other words, its shape is well described by a normal bell-shaped curve. All right. So, determine if there's an association between friendship potential and the sexuality of the person. So when people were rating friendship potentials, they didn't know if the person self-identified as gay or straight. So it'd be interesting to see, is there a difference in the typical friendship potentials between the people that self-identify as gay or straight? So we're going to use associate to do this analysis. We're going to compare the average values of the friendship potential between gay and straight people. And so we're going to run the command associate. We put the name of our y variable, twiddle, the name of our x variable. And in this case, if one of the variables is numerical and one is categorical, the y variable will always be the quantitative numerical variable. So our y variable in this case is friend score. I'll twiddle the x value. Where is this data living in? Well, it's in the FF data set, and we're going to use a seed of 2016. Okay, so we'll run this, and a whole bunch of different output. Here's side-by-side box plots showing you the distribution of friendship potentials based on whether or not the person was gay or straight. These stars represent the average values, and we know that's what we're comparing here. And we hardly see any sort of difference at all. So even if this association, even if the difference was statistically significant, it's probably small enough for us to just completely ignore. It's not a huge difference here. But let's do the analysis. What we want to do is we want to report the difference in averages and then report the p-value of this difference. So what is the difference in the averages? Well, if we look at the line corresponding to averages, we see that we have 2.947 minus 2.895 would be the result. So I'm going to just type that in, 2.947 minus 2.895. Run that. That's a difference of 0.052. That's a very, very small difference. Now, is this difference statistically significant? Well, we look at the p-value of this difference. Estimated to be 0.764 from 500 permutation data sets where scores and sexualities were randomly paired up with one another. And we're pretty confident the p-values between these two numbers. These are all much bigger than 5%, so we can conclude that there is not a statistically significant association. It looks like that there's no evidence for us to suspect that gay and straight people don't have the same fundamental average friendship potential. Looks like they're the same here. So what we say is that the difference in averages is about 0.05. It's very small. And the p-value of this difference is between 72.4% and 80.1%. So the difference is not statistically significant since this is larger than 5%. So there's no reason to suspect that fundamentally gay and straight people have the same average friendship potential here. We do see a small difference, but those differences can readily be explained by chance. And in fact, if we look at the histogram down here for the results of the permutation procedure, we see that the vast majority of the time, the number that we come up with for the discrepancy in the averages is much, much larger than the observed value, this small red line here. All right, the last part says, well, let's do some more association analysis, look to see if there's an association between the friendship potential and some of these other categorical variables. So one of which is apparent race. So we can just uncomment that line and run. And we see some difference in averages, some difference in the stars here, but it does not look like that difference is statistically significant because the p-values are bigger than 5% here. And we can just copy and paste, a whole bunch of these extra lines and just change the name of the x variable. So we're going to look at chin, whether or not the person had a prominent chin, cleavage, whether or not she was displaying her cleavage or not, clothing style, conservative or not so much so, glasses, wearing glasses or not, hair color, whether or not she's looking at the camera, whether or not the picture is a selfie, and then finally, if she has visible piercings. All right, so just going through them in turn, little bit of a difference between a pointed and a round chin here, but it doesn't look like that difference is statistically significant. What about showing cleavage? Notice a little bit of a difference. Girls showing their cleavage had a lower average value of friendship potential. Is this statistically significant? Aha, it is. So it does look like there's a statistically significant difference in average scores between the girls showing their cleavage and the girls not. So showing the cleavage is kind of a negative first impression, I guess, for whether or not you think you could be friends with her. Clothing style, what about that one? I'm going to put a little star that says statistically significant. I'm going to remove these guys. So we're looking at clothing style. We had conservative and revealing. So noticeable difference in averages there. Is it statistically significant? Ah, yes it is. So that one is also statistically significant. Less likely to consider the person as a potential friend if the clothing style is revealing. What about wearing glasses? I noticed a little bit of a difference in averages there, but the test is inconclusive because I'm not sure if the p-value is bigger than 5% or smaller than 5%. So in this case, I'm going to change the number of permutations up to 2,000 to get a better idea, to better narrow down what that p-value is. That'll take a little bit longer because it's got to generate 2,000 permutation data sets now. And let's see. We've narrowed down the p-value. Well, 5% is still right in there, so I'd have to even up it farther. do 5,000 permutations. Sometimes it's really a close call. And to determine what values of the discrepancy in averages that happen by chance, you really just have to make a lot of those permutation data sets where each of the values are randomly paired up with one another. But eventually you'll get a definitive answer there. So it just might take a little while. So while that's running, I'll uncomment these guys. And let's see the result. All right, so all these values, basically less than 5%. So yes, statistically significant. So there is a statistically significant difference in the average friendship potentials between women wearing glasses and not. Looks like wearing glasses kind of docks you some friendship potential points here. What about hair color? Above 5%, not statistically significant. What about whether or not she's looking at the camera or not? All above 5%, so it's not statistically significant. What if the picture's a selfie versus not a selfie? That's a pretty noticeable difference right there. And yeah, that's really statistically significant. P-value is much less than 5%. So it does look like, if the picture is a selfie, much lower average friendship potential than if the picture was not. Interesting. Piercings. All right, all above 5%, so not statistically significant. So what do we say? We say that the statistically significant associations are significant associations with cleavage, clothing style, glasses, and selfie. All right, so if we are in advertising and we're designing a spokesperson and we want this woman to be looking like she'd be a potential friend, we want to make sure that she's not showing her cleavage because that kind of docked friendship potential. She's dressed relatively conservatively, revealing kind of docked the friendship potential as well. She's not wearing glasses because that had lower friendship potential, and making sure that the picture doesn't look like it's a selfie because that had lower friendship potentials as well. All right, so we're good to go. We can click knit HTML and it'll go ahead and make the HTML document. You could knit to Word, mess with the formatting. And the one thing you have to make sure of, if this fails, to make sure that in the R Markdown kind of dialog box, that it is looking in the folder where your data file is, the one that you were loading in the FF friendship potential data set. If it's in the downloads folder, which is pretty common, you click on the link, it puts in the downloads, you open it, you start working from it. Since the file and the data file aren't living in the same place, it'll come back with an error saying, hey, I couldn't find this file, so try again. Just make sure that the RMD file and the data files always live in the same folder. So notice this is taking really quite a while to actually knit, and in this case the reason why is because these commands took a long time. When RStudio makes a document, it goes through and runs all that R code, so if that R code took a long time to actually run, yeah, it's going to take a long time to compile it. So we got a lot of output, and we're good to go.